Yeah, this is a talk about porting the COSMO weather model to Manycore CPUs. So I'm Felix Thaler. I'm working as a software engineer at CSCS, the Swiss National Supercomputing Center, and this work was actually a collaboration between CSCS, Swiss, and also the Scalable Parallel Computing Lab at ETH. So, a small outline. First, I'll introduce our chosen Manycore architecture, which is the Intel Xeon Phi KNL. And so don't be disappointed. This hardware has been discontinued by Intel and might seem a bit outdated, but actually there are other similar architectures coming or already on the market now. So should still be kind of interesting. I'll also give a very brief overview over the COSMO weather model. Of course, show how we ported the dynamical core and show some results. Our chosen Manycore architecture was the Intel Xeon Phi Knight's Landing. Typical for a Manycore architecture, of course, it has many cores. Some models up to 72, so the model available at CSCS has 64 cores. Each core has up to 4 hyperthreads, so you can configure between 1, 2, and 4. There are 16 gigabytes of high bandwidth memory with up to 470 gigabytes per second measurable stream bandwidth. There are additionally up to 384 gigabytes of DDR4 memory, but I will never talk about those in here because for the weather and climate applications, which are mostly memory bound, we didn't care about this slower memory. Then there are wide vector registers, so AVX 512. And in contrast to GPUs, there is full cache coherency. And the full hardware actually looks a bit like this. So there are 72 tiles with, 36 tiles with 2 cores each. So 72 cores in the largest version at least. And they are ordered in such a mesh or grid arrangement, and communication between the tiles actually goes along those vertical and horizontal lines in the mesh. This is actually the biggest difference compared to the previous architecture, the Intel KNC, where all communication was on a ring bus. So this was a great improvement because the cache coherency costs quite a lot with such many cores, and on the KNC often actually the communication in this ring buffer was very slow. We chose this architecture because when we started with the project, which in the end was a past paper last year, was quite new. So we started in 2017, and the hardware was released in June 2016, actually at the same time as the NVIDIA Tesla P100, which is used in CSCS flagship system PITSTime. And both of the architectures have 16 gigabytes of high bandwidth memory. The KNL slightly slower peak bandwidth than the P100, and also fewer flops, but also here the flops don't matter much for weather and climate codes. So the COSMO weather model is actually a non-hydrostatic limited area atmospheric model developed by the COSMO Consortium, which stands for Consortium for Small Scale Modeling, and currently, or I think from the start, have all these countries, so Germany, Switzerland, Italy, Greece, Poland, Romania, Russia, Israel being in the consortium. And they started developing that model in, I think, 1998 or so. So it's a pretty old model, but still used in production today. It uses a Cartesian latitude-longitude grid using finite difference, discretization. And the special thing about this model is actually that it has been running on GPUs since 2016 at Meteo Swiss, and was thus the first weather model running in production on a GPU system. And this was achieved using different strategies. So the whole model is written in Fortran, as probably most of the weather and climate code is still today. And a typical time step looks like this. This is also typical for other weather codes. So you have one part which is called the dynamical core. This is actually the Navier-Stokes solver. So really solving the movement basically of the air and everything else. And then there's another part here before the dynamical core, the physics part, which is also quite computationally intense, which solves only column-based computation. So it's a bit simpler. And this thing called physics, so those are usually some models solving radiation or precipitation or whatever, some other parts, so less dynamical part or things that can be approximated locally. And as this features simpler access patterns, this could be ported using OpenACC to GPUs. On the dycore, of the other hand, which is much less code, but 60% of the runtime, the access patterns are quite complex. So those are usually some compositions of stencils and things. And this was not possible to port efficiently using OpenACC. So this is based on the GridTools C++ embedded domain-specific language. Previously, so the initial version was actually run on Stella, the predecessor of GridTools, but with very similar concepts and performance. And so what we actually wanted to do, or our target to run this dynamical core implemented in GridTools on the Intel KNL, was just to develop a new backend for GridTools. So no changes on the dynamical core, but just on GridTools. But the question was how to get there. So we identified two main motifs, or this was actually done already before, and it's quite simple. So there are usually in most weather codes is actually the same, as long as they use some kind of finite difference, finite volume, finite elements, or whatever explicit discretizations in the horizontal, and implicit discretizations along the vertical, which is usually done because you have much smaller grid spacing along the vertical, so you don't want to restrict your time steps by the vertical, so basically the thin vertical layers you have to use to get a good resolution on your atmosphere. So the motifs come from this discretization, and actually the vertical computations are usually quite local, so they are tridiagonal solvers in most cases, while the horizontal stencils differ a bit, but yeah, are just coming from the explicit numerical discretizations. So we chose two representative patterns. One is horizontal diffusion, one is vertical advection, and we manually optimize those computations to gain insight, so how to optimize horizontal computations in general, vertical in general, and then we apply those insights to the DSL backend, GridTools backend. So horizontal diffusion, as I said, purely horizontal dependencies, so embarrassingly parallel. It's actually not a single stencils, but it's a composition of a Laplacian, two flux computations, and flux limiter and a flux application, and relatively straightforward to implement. So you can here see performance results, which are pretty good for the KNL. So the darker gray area, so 64 squared by 80 to 128 squared by 80, grid points were back then at least actually the relevant domain sizes for the local forecasts by Meteo Swiss. So they are pretty much on par there, and the KNL is even a bit faster on larger domains. So this looks pretty good, and was a bit of a surprise because the peak bandwidth is still a bit lower on the KNL. And the most important trick we had to apply, so the naive version was pretty bad, but the most important thing was just to don't store any intermediate result in memory and compute redundantly everything on the fly that's needed for the final output of the stencils, to not put any pressure on the KNL's caching or cache coherence system and memory system. For vertical advection, results were even better for the KNL, at least on the small domain sizes that were looked at as relevant for the local area simulations back then. The KNL outperformed the NVIDIA P100 quite significantly, but there were some issues. So on the larger domain sizes, as you can see here, there's suddenly a drop in performance. And the reason is actually that for those domain sizes, software prefetching that was used along the vertical failed. So you can prefetch a memory location which is not on the same page. So in this case 4 kilobytes away. So on larger domain size, where actually the strides are bigger than 1 page, it just fails. And this actually, so the drop would even be larger if you use the same implementations for small and large domain sizes, but here the graph shows just the best implementation. So by using a different implementation that's not as good as the fastest one on small domain sizes and a bit slower than the NVIDIA card still on the large domain sizes, you can get a smaller drop. There would actually be probably a much better implementation or much better data layout, but if we could block the storages, but with grid tools it's not possible to block the storages. Otherwise it would make sense to block storages with a cache line or vector size, which is actually the same on the KNL. Such that we could use hardware prefetching along the vertical and vectorization. So the important part is we need to use prefetching and vectorization to get full performance. Yeah, and a bigger issue for us was also that the optimal data layout for the horizontal and vertical stencils are different. So we already knew here that we can't get full performance probably when using, so on the real world code, when of course we don't want to change data layout between each computation. So we learned quite a bit here already, so we should avoid any load on the KNL's memory subsystem. Often it's much better to compute something twice than to cache it in memory. And this is also true for many other modern hardwares, just because the computation power always goes up, but the memory systems don't become faster anymore, or not much faster, not as much faster as the computation power. But we have also seen that the Manycore CPUs can actually competitive to GPUs, but actually only if you invest a similar amount of effort. So if you just run the old CPU code, like Intel marketing team wanted us to believe on those new hardware systems, it's not fast. So you have to really optimize for those. And what's also interesting that actually the KNL acts quite similar to normal CPUs, but the characteristics are quite exaggerated. So a normal CPU sometimes you might, or normal on classical CPUs, you sometimes may be able to actually have some code non-vectorizing, but if you have good use of software prefetching, it might still be quite fast, of hardware prefetching. Or if you cannot use hardware prefetching, but use vectorization and have an access pattern such that your cache reuse is quite good. It might work without prefetching already quite fast, maybe not optimally, but quite fast. But on the KNL, you actually lose a lot of performance if you just screw up vectorization or prefetching. You can get really only a tiny amount of the performance you could get if everything would work as it should. So yeah, next step was of course implementing the KNL backend using those findings. We already knew that the performance should be significantly worse than what we have seen in this standalone experiments. First, we should lose about 15 to 25% probably in horizontal stencils because we can't use the optimal layout there, because we chose the vertically optimal, because they're more expensive vertical stencils than horizontal in the COSMO dycore. Further, there's probably quite a significant loss on the vertical stencils because we could not implement the software prefetching in a useful way that was working with grid tools. Yeah, in general, as most of you may know, that it's actually always or almost always non-trivial to get software prefetching to work. And in the COSMO dycore, there are many different vertical computations, so there was no general rule of thumb that we could apply. So when we tried it, usually we could just destroy the performance, but we couldn't get any general improvement with software prefetching in the grid tools backend. There might be an additional loss due to missing non-temporal stores on the grid tools backend. We don't use non-temporal stores, while in the standalone examples this was very important, so that you could get to full memory bandwidth. You have to use non-temporal stores on the Intel architecture, but the problem there is that actually those non-temporal stores invalidate the caches on the store. That's not what we want. So why we use them is that we don't have to load to the cache, but we actually would like to have the result afterwards still in the cache for the dycore, because in the next iteration or in the next stencil, most probably we will use the result of the previous stencil. And there are of course some further smaller things. So in the grid tools backend, we just use empirical block sizes. We don't do auto tuning that we have been using on the standalone hand optimized codes. But in the end, actually, the performance was even worse than expected, probably. So it was about a factor 2 off. So here we can see the NVIDIA P100, the KNL, the NVIDIA K80, and Skylake measurements, and actually the individual colors or individual computations in the dycore. And you can see some that actually are just a bit slower, almost the same speed on the KNL, and some like the dark blue one, the second from below, is much slower on the KNL and on the P100. And of course, we were not very happy about this result. It was quite a bit slower than we hoped for. And of course, we investigated a bit and found some good reason why this was actually the case. And main reason was that most computations are actually written in a GPU-friendly way. So for example, they store results in shared memory, which is quite fast, especially on those GPUs. And more modern one, we might use a different optimization actually. But for KNL, or for the grid tools backend of the KNL, this meant that we also had to use memory buffers for intermediate results, which we have seen previously is actually a bad idea for many cases. So probably we could have achieved better results on the KNL using grid tools, but this would have meant that we had to rewrite the kernels, because actually the COSMO, the user code, because this was actually implemented in a GPU optimal way, but not in a KNL optimal way. So actually the result or the main result we got here is actually that the grid tool C++ DSL is not really fully hardware agnostic, because it does not only describe what should be computed, but to some extent also how. This is of course hardware dependent and does not allow to run on all hardware with the optimal speed with the same code. So, small summary, we have a same user code running on CPU and GPU. This is quite nice, but we actually hit the limits of this of the grid tools, or the C++ embedded DSL approach. We hit the limits of probably language design of grid tools, but also limitations of C++ compilers. So there was quite some debugging involved to make everything work more or less smoothly. But even then, actually this suboptimal dycore implementation of the KNL is as fast as the Fortran, so as the original Fortran implementation run on the KNL. So we haven't lost any performance on this conversion to the DSL when run with the KNL backend. And the same code can be run on the GPU with very good performance. And that also some side effect was that the new backend is actually not only good for KNL, but also in other more modern CPU architectures like the Skylake and also the current AMD architectures, and of course the A64FX and similar things. So some discussion why we actually want to use domain-specific languages. Main point is for sure that we want to have a single user code, so we don't want to duplicate actually the original code for each new hardware, which will of course lead to a huge code duplication and just impossible maintenance effort. And we want also split from model developers, so climate scientists, atmospheric scientists that should be responsible for the numerics, but they should not be responsible for performance. But instead, some performance engineer should actually care about the performance while not caring about the numerics. One point is, of course, also the easy adoption to new hardware, which is kind of a similar thing. So the user code should not need to be changed, but just some backend code, which is in the end hopefully much smaller if multiple weather models, for example, use the same DSL, and should be much easier than changing a whole weather model. And of course, we also want to have high performance with a nice code quality, so easy to read and also easy to write for domain scientists. And we were partially successful probably. So we have a single user code that runs on CPU or on KNL and GPU, and actually also CPU. The adaptation to the new hardware was quite simple, especially for the user code. But in the end, it was not that performance portable. So we reached a limited performance portability. But we know it could run much faster. So yeah, we were not too happy with that, but still it's as fast as the original Fortran code. So it's not too bad. So there's some kind of performance portability, but of course we want to be faster. And also the last point, so the code is kind of readable for C++ programmers. But we noticed that actually climate scientists, domain scientists, they don't like to read nor write this code. So they didn't want to use grid tools. And so actually the future we are now investing in is GT4Py. So it's basically grid tools for Python. It's a user-friendly, I would say, higher level DSL. So it's a domain-specific language embedded in Python. It's developed at CSES in collaboration with the European Center for Medium Range Weather Forecast, ECMWF, together with Vulkan, who wants to port GT4Py their model, the FE3 model, an American model to GT4Pi. And of course, also the ETH is involved, especially for performance questions. So several of your group are probably also involved here. And we have various backends there in GT4Pi, so this is very nice. We have NumPy for fast prototyping, and there have been several workshops now with domain scientists. So the domain scientists actually like to write the code in Python. They like to read that code. They understand that code. They can easily work with it. And with an NumPy backend, they can just run everything as normal in Python, and it's not that fast, but for debugging, it works well. They don't need to install any fancy dependencies or anything, so easy to use. Then there's also a Grid Tools C++ backend, which allows to run the code on GPUs, so it's already much faster than the NumPy backend. And the user doesn't really notice anything from changing the backend. So it's the same user code, just changing backend at some point, and it will run much faster. At least the computation itself, if you generate, of course, code, this code has first to be compiled. So first generated, compiled, and then linked to Python to make it callable from Python. And currently there's also work on a DAIS backend. So we already have an implementation of a DAIS-based backend, which in the end hopefully should allow for very nice data flow optimizations and execution time similar to hand-optimized codes. And our goal at CSCS is actually to get a global cloud resolving. So this means 1 kilometer global resolution for climate simulations, which is quite a tough goal, but we want to reach it in the next few years, and certainly in using the next so the successor of Pitstain, the next flagship system of CSCS. Yeah, that's it. Thank you for your attention.